Real exam questions. This is question 57 about beam design. Determine in the serviceability limit state the steel stress in the lower and upper reinforcement of a rectangular section under bending plus tension. So it means domain 1A, under bending and tension. First derive the formulas and then apply them to the example of bending moment equals to 34 kilonewton meter, normal force 180 kilonewton in tension, tension reinforcement 2 diameter 16, compression reinforcement 2 diamonds 10, concrete coverage 40, the clear up diameter is 10, steel and concrete quality are given, and the beam is 200 millimeters width and 600 millimeters as depth. So now let's look at the forces and stresses. We have the tension reinforcement and compression reinforcement. So when we look at the forces, we know it's an eccentric tension. So NSD is offset with a value of E0. This is the force in the compression reinforcement with its position D2, and this is the force in the tension reinforcement with the position D1. So just for clarity, I'm not using negative or positive signs just to make it clear. It's FS1 works in this direction and this in this direction, so those two are tensions, but the value of FS1 and FS2 is a positive value. Then we take the rotation equilibrium around the tension reinforcement, which gives you, of course, Fs2 times this distance, which is d minus d2. And this must be equal to NSD times this difference, which is, of course, h over 2 minus E0 minus V1. So this equation, this is the green part of the equation, which is the reaction, and the action is on the other side. So action equals reaction. Then the rotation around AS2, around the compression reinforcement, it's the same type of formula, but now it's Fs1 times this lever arm equals NSD times this lever arm. The stress in the compression reinforcement is, or I should say, in the reinforcements 2, because this can be compression and tension. We don't know yet. The stress in the upper reinforcement is then the force times divided by the cross section, but the force we know from the rotation equilibrium around the tension reinforcements is equal to this. So now we have a formula for the stress in the upper reinforcement. The stress in the lower reinforcement is, of course, the force in the lower reinforcement divided by the cross section. And again, Fs1 can be substituted with this equation. Now we will make an application with the different elements of the example. Bending moment and tension, normal force tension is given. The reinforcement AS1 is 402 square millimeters, and AS2, the compression reinforcement, or the least tension reinforcement. Or I can also say this is the least compressed reinforcement and this is the most compressed reinforcement. So it's 402 and this is 157. The eccentricity is then, of course, the bending moment divided by the normal force or by the tension, and gives us 189 millimeters. The stress in the lower reinforcement is then equal to the formula that we found on the previous slide, with H is 600, B is 200, C is 40, clear up diameter is 10. So we can now put in the different variables. For instance, d min d2, it is just d is the total depth minus concrete cover minus stirrup minus point of gravity of the reinforcement. And we find 400 megapascal. And the sigma S2 in the top reinforcement, we can just put in the numbers and we will find 125 megapascal. So in SLS, the beam under bending moment and tension gives you a stress of 400 megapascal in the lower reinforcement, which is just admissible. The normal admissible stress is 400 megapascal. And the compression reinforcement is okay.